It's my absolute pleasure to be here in front of this amazing audience in this beautiful venue and to kick off PWL 2018. So I have a lot of interesting stuff that I want to share with you, so let's just get started without further ado. Concurrent programs, as we all know, are ubiquitous. They are everywhere, from our cell phones to our cloud platforms to our device drivers and so on. And unfortunately, concurrent programs are really hard to reason about. And the main reason is that there is a combinatorial explosion of interleavings that one has to think about, which is referred to typically as the dreaded interleaving explosion problem in concurrent programs. And so unsurprisingly, concurrency bugs are almost as common as concurrent programs. You write a concurrent program, you introduce a bug, and these are fairly subtle and hard to debug. In fact, two of the most catastrophic failures that we have seen due to software bugs, the Therac 25 radiotherapy machine overdose disaster and the 2003 North American power blackout disaster, were both, at least in part, due to concurrency bugs, in particular race conditions. So you might already know this, but it's interesting to actually note that many of these bugs, such as atomicity violations, race conditions, deadlocks, live locks, and so on, are actually due to errors in synchronization. Okay? So wouldn't it be wonderful if you, as a programmer, just had to write an unsynchronized program with no synchronization and only make sure that the program is correct, that it meets its specification when the threads are executed sequentially, and then this magical synchronization synthesizer steps in, inserts synchronization, and makes sure that the final concurrent program is correct with respect to the specification. So this is the dream of computer-aided concurrent programming, and it has something that has captured the imagination of multiple researchers over several decades, going back to the early 1980s. And this is the focus of today's talk. So I'm going to take you through 3 papers, only one of which is mine. The first is an old seminal paper from 1981, which was one of the early papers, if not the earliest paper, on synchronization synthesis. The second is a relatively recent paper from 2010 with a particularly cute idea that I like. And the final, the modern approach, is work that I have completed fairly recently with my collaborators. So let's get started with the seminal paper. So this is a paper that I'm hoping many of you, or at least have at least heard of. So this is Design and Synthesis of Synchronization Skeletons Using Branching Time Temporal Logic by Ed Clarke and Alan Emerson from 1981. This is the paper that introduced model checking, which was later recognized by with a Turing Award in 2007, and has nearly 4,000 citations if you check online. So if you actually look at the title, okay, and if you take a look at this paper, however, you will notice that this is almost entirely a synchronization synthesis paper. Okay, so here is an instance of a paper that set out to solve the synchronization synthesis problem and ended up presenting a really elegant solution for it, but along the way founded this Turing Award winning area as it was solving the synchronization synthesis problem. So funny how certain things can turn out. Another fun fact is that this paper was actually Alan Emerson's PhD thesis, which he did with his supervisor, Ed Clarke. So that's really amazing. This was really his thesis work. And Alan, who was also my PhD advisor, however, always often mentioned the burden of having a famous first paper. That's something that's always hard to live up to. It's an interesting thought. I think I could have lived with that. So let me give you a bird's eye view of this paper. One-line summary of this paper. This presents an algorithmic framework to check if certain finite state transition systems satisfy some temporal properties, and also to synthesize synchronization with respect to temporal properties for such systems. Okay, so that's the one-line summary. Let's take a closer look. Processes in this paper are what are called finite state synchronization skeletons, which are labeled transition systems that essentially capture the concurrency in the program and suppress details that are irrelevant to synchronization. For instance, a process could be doing a bunch of local computation which is irrelevant to synchronization, and that is all abstracted away into one node in this finite state labeled transition system. The communication model is a shared memory model, which we all know. It's also interleaving based. Let me just clarify that. So this means that a concurrent execution consists of an interleaving of events from different threads or processes, where exactly one thread takes a step at a time. Okay, these threads might be scheduled by a non-deterministic scheduler, but exactly one process makes a step at a time. The specification is temporal logic, and I will give you a brief preview of that shortly. The synchronization is synthesized in the form of what are called guarded commands, which are essentially atomic actions labeling the transitions of the transition system, where the semantics is that the transition can be taken only if the guard is true, and in which case the command, which is essentially an assignment of values to some variables, is executed along with the transition. Okay? And finally, the procedure is Tableau based, and I'll show you a preview of that as well. So here is the paper in action on an example that the authors worked out in the paper. So this is what I mean by a process's synchronization skeleton. It just consists of 3 states and is fairly simple. Here is the complete specification of the expected concurrent behavior of this program in temporal logic. Okay, so this includes global properties expected of the concurrent program, such as mutual exclusion or starvation freedom. Also, it includes a precise characterization of each process's behavior in temporal logic. So it says things like each process is in exactly one of these 3 nodes or code regions at any given point of time, and so on. So this is a complete specification of expected behavior. And what this paper generates, given this input, is a final completed synchronized skeleton that looks like these. So these are 2 processes where the transitions are labeled with guarded commands. For instance, here, this guarded command means that this transition can be taken when try2 holds, and this transition also sets the value of the turn variable to 2. Okay, the concurrent composition of these 2 synthesized processes is guaranteed to satisfy this temporal logic specification. So this paper, I just want to emphasize, goes much beyond synchronization synthesis. It's helpful to recognize that it made several contributions, such as introduced a new branching time temporal logic called computation tree logic, CTL, which we will see next. It introduced the model checking procedure, which is a procedure for checking if a finite state transition system satisfies some CTL property. It also introduced a general procedure for synthesizing a model of a CTL formula, for synthesizing a structure that satisfies a CTL formula. So let's do a quick primer on temporal logic then. So temporal logics are used to reason about behaviors of programs that are essentially non-terminating ongoing systems with infinite behaviors. And these processes are modeled, these programs are modeled using what are called Kripke structures, which are finite state labeled transition systems, as shown here, where the nodes are labeled with atomic propositions. Okay. So now, where does the infinite computation crop up? Well, if you unwind this Kripke structure and essentially look at all the computations that can happen in this structure starting from the initial node, you get this infinite computation tree, which is what's called a infinite tree, which is called a computation tree. Okay? And temporal logic is perfectly suited to express properties of such infinite computation trees. So what does CTL look like? CTL is just one class of one kind of temporal logic. There are many others out there in the field. So this is what a CTL formula looks like. A CTL formula is something that holds in a state of a crypt key structure and is built from atomic propositions, Boolean logical connectives, and these extra quantifiers that you see on the right, which are called path quantifiers, A and E, referred to as always and exists. Okay, so informally speaking, we say a state satisfies the formula AF if along all paths starting from that state, F holds. Similarly, we say a state satisfies EF if there exists some path starting from that state along which F holds. Okay? So what is F now? It isn't there in this grammar. Well, F is what we call a path formula, which is a formula that holds that holds in a path starting from a certain state. It is built using these operators called temporal operators. This is the next time, eventually, global, and until operators. And I don't want to dive into the formal semantics of CTL. What I want to do is just show you some simple examples of what it means for a structure to satisfy a CTL formulas with some simple examples using our computation tree from before. Okay. So here's the first temporal logic formula I want to show you, which is AGQ, which essentially holds in any state from which along all paths that are starting at that state, Q holds along every state in each path. Okay, so this essentially means that Q holds everywhere. And all the nodes in this computation tree that satisfy, all the states in this computation tree that satisfy AGQ are marked in yellow. Okay, so for each state along each path, Q holds everywhere. Okay, that's AGQ. This is a classic safety property. Another interesting property is CTL formula is EFP, which is a classic liveness property, which holds in a state if there exists a path starting from that state along which P holds eventually. Okay. We again remember that we are reasoning about infinite executions, and that's why we can say things such as eventually. So these are all the states in this computation tree that satisfy EFP, because from all of these states there exists a path to a state that satisfies P, either because the state already satisfies P or there exists a transition from a state into a state satisfying P. Let's look at one final formula which is slightly more complex, which is essentially a nesting of the previous two formulas that we saw, which is EF, AG, Q, and R. This says this holds in a state if there exists a path from the state along which you can reach a state from which AG, Q, and R holds eventually. Okay? So this is a nesting, and all the states in this computation tree satisfy this formula. Well, how do you see that? This is a little bit complex, and in fact, a model checking procedure can really decide this automatically to see if a structure satisfies such a formula. Here is what you do. You essentially look at the smallest sub-formulas and then build up the set of states satisfying the formula. So you start with states that are that satisfy Q and R, the simplest sub-formula in this formula. Okay, these are all the states. Then using this set of states, you build the set of states that satisfy AG, Q, and R, which in this case happens to be the exact same set of states. And finally, you can then figure out the set of states that satisfy EF, AG, Q, and R. So all the states that have a path to some state in this set of states. Okay, so that's EF, AG, Q, and R. So that's all I want to say about temporal logic. I do not have time to go into the model checking procedure. I also don't have time to go into the CTL synthesis procedure in depth, but I'll try to give you a glimpse of what that procedure was like. So this is a decision procedure, which means that it gives a yes or no answer to a question. The question is this CTL formula satisfiable? Well, then the procedure answers no if the formula is not satisfiable, and yes if the formula is satisfiable, in which case it also returns a model or a structure that witnesses satisfaction of the formula. Okay. So these are the basic steps of the CTL decision procedure, where the first step you construct what is called a tableau, which in some way encodes all the possible models of the CTL formula in question. Okay, this is an initial tableau. Then in the next step, you check this tableau for inconsistencies and delete any inconsistent portions of the tableau. If you end up deleting the root node, then you declare the formula to be unsatisfiable. Otherwise, you can extract a model of the CTL formula from this tableau and then return that the formula is satisfiable along and return the model. Okay, so here is what a tableau looks like. So this is a tableau for this CTL formula EFP and EF0P, which labels the root node of this tableau. I'm not going to explain how to build this. The construction is very mechanical, but it's unfortunately out of scope for this talk. I need you to note two things. This tableau is essentially a directed graph consisting of what are called OR nodes and AND nodes. And what the semantics of the tableau is that every node, when interpreted as a state in some suitable structure, like the final model, essentially satisfies all the formulas that are that the node is labeled with. Okay, so these, for instance, these labels, these are the AND node successors of this OR node, and they are all the different ways in which this CTL formula can be satisfied. Okay, but I want to leave it at that and move on to the next step, which is deleting inconsistent portions. There is just one node here which has an inconsistency. It requires satisfaction of both P and not P in the same node. So we delete that. Everything else is fine and can stay on. The root node is still hanging in there, so we can extract a model from this tableau. And here is how you can construct a model. Well, you can start from any of the remaining AND nodes. You can take your pick. There is no, you don't have a unique model. There can be several. Let's say we pick this one. In this node, P holds, so P is satisfied, and hence EFP is satisfied. But it says that we still have an obligation to satisfy EF not P in the next step. And to do this, we follow its successors and obtain this AND node in which not P is satisfied. So you're essentially splicing together all the AND nodes from the tableau, making sure all the eventualities are fulfilled to capture the model. This is what the final model looks like. It's fairly simple, but there was a complex path to arriving at this model. So that is CTL synthesis, but I was actually going to tell you about synchronization synthesis. So how do we go from here to synchronization synthesis? Well, as I'd mentioned before, what you do is you write a complete specification in temporal logic of the entire expected concurrent behavior of your program. This is what's shown here. And then you use the previous tableau-based method to construct a global model of the concurrent program. And finally, you factor this out into these completed synchronization skeletons where the transitions are labeled with guarded commands. Okay, so the essence of this synchronization synthesis procedure is really the ability to do CTL synthesis and the ability to specify your entire behavior in temporal logic in CTL. So that concludes my discussion of the first paper, which really was remarkable in many ways, especially for its time. But it had some fallacies which actually came to light later. In particular, this complete specification that I have been emphasizing on is a very strict requirement. It's not always possible to justify the need for writing a complete specification in all scenarios. For instance, a programmer may not be an expert in temporal logic, or despite his or her best efforts, a programmer may just due to oversight skip describing the intended behavior in temporal logic. So this is a problem in general. Also, the framework only applies to finite state processes, and it doesn't really address the interleaving explosion problem, because the Tableau actually builds the entire global model which corresponds to the product graph of all the processes, which is all the interleavings in the program. So let's see now if our next paper manages to address some of these issues. So this is a paper by Martin Vechev, Eran Yahav, and Greta Jorsch. This is Abstraction Guided Synthesis of Synchronization from POPL 2010. The one-line summary of this paper is that it's an abstraction-based approach to infer synchronization to ensure safety properties of infinite state concurrent programs. Okay, so you've hopefully already noticed some differences from the previous paper. So here's the closer look. This addresses the restriction that the previous paper had about the systems being finite state and tackles infinite state programs. Okay. The communication model stays the same. The specification is no longer a general temporal property, but is simply a safety property. And this really simplifies the process. Also, the specification does not need to be complete, okay, which is a win. The synchronization is now synthesized in the form of atomic sections. I guess you're all familiar with atomic sections. Their semantics simply ensure that any code enclosed within an atomic section executes uninterrupted. Okay. And finally, the procedure which we look at is based on abstraction, refinement, and counter examples. So here is again the paper in action on an example from the paper where you have a concurrent program, a multi-threaded program with the safety property expressed as an assertion within the program. Okay, this synchronization synthesis procedure here, apart from the program and the specification, also takes in some abstract domains to help with the abstraction refinement, and generates a concurrent program with atomic sections. So here is, for instance, a representation of an atomic section which says that these two events in thread 2 have to execute atomically. Okay, and this is again guaranteed to satisfy this assertion over here. So that's the snapshot. And again, this paper has contributions that go beyond just synchronization synthesis. For instance, abstraction guided synthesis is an idea that I really like in this paper that applies to a much broader context. They have a great instantiation of it in this paper, of course, but it really can be applied to other synthesis domains as well. This paper also presents clever instantiations of two ideas that are not necessarily new in this paper, which is that of counter-example guided synthesis or synthesis as repair, and then quantitative synthesis, where you also add a quantitative objective beyond your correctness property to help choose between multiple possible candidates for your synthesis. Okay, and we will take a look at these. I mean, you should keep an eye out for these concepts when I'm explaining this. So the main idea of this paper is that it combines two classical frameworks for verification and for repair or synthesis in a neat way. So here is a classical framework for verifying infinite state programs using what is called counter-example guided abstraction refinement. So what's the basic idea here? Well, you take a program and a correctness specification and some abstraction, which results in a sound over approximation of the program, and try to verify this abstract program. Okay? If you succeed, then you're done, because it's an over approximation of all the behaviors of the program. Otherwise, you get what is called an abstract counter-example, which may or may not correspond to a concrete counter-example from the original program. In fact, the counter-example might have arisen because your abstract domain was really coarse. So what you then do is you refine the domain in order to eliminate this counter-example and repeat the process until your verification succeeds. Okay? So that's CGAR, or counter-example guided abstraction refinement. Now here is a somewhat analogous loop for doing counter-example guided repair or synthesis, okay, where the goal is to modify an incorrect program so that, or a partial program in a way such that it ultimately satisfies a specification. And you do this using counter-examples. You try to verify it, it fails. You get a counter-example, you modify the program, you extract some constraints that correspond to the program's restriction that can eliminate the counter-example, and repeat the process until your verification succeeds. Once this succeeds, you take all of these accumulated constraints and then implement them in the original program to get your final modified program. Okay? So that's counterexample guided repair, and this is the combination of these two approaches that is presented in this paper, which is abstraction guided, counterexample, how do I say this? This is abstract counterexample guided synthesis, okay? So here, the goal is essentially to get to an abstract program that satisfies its specification. So what you do is, when you get an abstract counterexample, you exercise one of two choices. You either refine the abstraction in order to eliminate the counterexample, or you modify the program in order to eliminate the counterexample. Okay? So what this, the advantage of this over the previous two independent techniques is that you just get more degrees of freedom. There, you could get stuck if you were just doing one of these loops, because you could reach a juncture where you cannot refine the abstraction anymore, or you could reach a juncture where you cannot make the program, restrict the program anymore, and this just enables you to have more degrees of freedom in ultimately getting to an abstract program that satisfies the specification. Okay, so this is the cool idea in this paper. I think my slides are running amok. Okay, let me slow down a bit there. So the framework here is a broad framework. It has nothing to do with synchronization synthesis so far. The way it is instantiated for synchronization synthesis is really in the way these constraints are gathered. Okay? Everything else can be fairly generic. This framework can take generic abstract domains, generic techniques for doing refinement, and so on. The way it does this restriction is essentially take an abstract counterexample and gather some atomicity constraint that can eliminate this counterexample. So let's see how that might work. Here is a visualization of an abstract counterexample. Okay, hopefully this is not too abstract. Here are two threads. Okay, and these are the events in the first thread. These are the events in the second thread. Here is the interleaving between the events of the different threads. So there are three context switches here, and this is an error state. Okay, so this is an abstract counterexample. Now, if you want to eliminate the counterexample, there are actually many ways to do this, but one way to do this is by essentially disallowing these three context switches that happen here. Okay, and you can disallowing this by essentially enclosing the events between which a context switch happens within an atomic section. Okay, so here are three atomicity predicates corresponding to this constraint, the constraints that ensure that these two events from this thread execute atomically, and so on and so forth for the others. So there are three essential context switches in this interleaving. The last one doesn't really matter. And the overall atomicity constraint that you can extract corresponding to this abstract counterexample is essentially a disjunction of these three atomicity predicates. So this says that you can eliminate this counterexample by enforcing the first atomic section, or the second one, or the third one. Either, I mean, no matter what you do, you would have eliminated this particular interleaving of events. Okay? In general, an atomicity constraint is actually a bunch of conjunctions over such disjunctions, because you are accumulating these over multiple counterexamples, but let's leave it at that. So that's how you get an atomicity constraint, but perhaps you might notice that an atomic section is actually fairly conservative. So besides eliminating the counterexample that you are interested in eliminating, it also ends up eliminating many traces that are possibly correct. Okay? So what this framework does is, once it has accumulated all the atomicity constraints that can ensure correctness, it poses a quantitative synthesis problem that tries to synthesize a minimum, not a minimum number, but it tries to minimize the size of these atomic sections so that it permits as many concurrent behaviors as possible. Okay, so there is a quantitative objective that essentially encodes the size of atomic sections. So that's this abstraction guided synthesis framework, and here is again the framework in action. now perhaps these abstract domains make more sense, so you need to supply the initial abstract domain and perhaps all the abstract domains you might want to go through in your refinement as well. Again, this is a neat idea, but it has some shortcomings. It also actually does not do anything to tackle the interleaving explosion problem. Okay, so it does handle infinite state concurrent programs, which is great. It does not require a complete specification, which is great, but it still does not really tackle the interleaving explosion problem. It uses abstract domains to actually target the state explosion problem. Your data might have an infinite domain, and it enables you to tackle that, but it does not do anything to tackle the interleaving explosion problem. Also, even though the specification is not required to be complete, someone still needs to write these assertions. Someone still needs to figure out what is the intended behavior of the program, and this can be challenging in some contexts. Finally, as we discussed, atomic sections are not very permissive. Okay, so let's see now if the work that I did recently with my collaborators can address some of these issues. So this was work done with a great group of collaborators as part of my postdoc, which I did with Tom Hensinger in Austria. This is, oh, you might notice, by the way, Ed Clarke, who is one of the co-authors. So this is the same Ed Clarke from the first paper. So he has been doing synchronization synthesis from 1981 to 2016. So this is from non-preemptive to preemptive scheduling using synchronization synthesis. This was our CAF paper from 2016. This was actually part of a series, a small series of papers that included a POPL paper from 2016 as well, called Succinct Representation of Concurrent Trace Sets, and a subsequent follow-up journal paper published in Formal Methods in System Design last year. Okay, so some of the ideas that I'm going to present are not just from the CAF paper, but from these two papers as well. So here's the one-line summary of this paper. This is a trace generalization-based framework to infer synchronization for an implicit specification for infinite state concurrent programs. Okay, so this is trying to tackle some of the problems of the previous papers. Here, let's take a closer look. So the processes and communication model are exactly the same as the previous paper: infinite state, shared memory, interleaving based. The specification now can definitely be a safety property, but we also have the ability to reason about a specific kind of implicit specification, which was suitable for our application domain of device drivers, where the specification is essentially based on behaviors that are possible under a friendly non-preemptive scheduler. The synchronization here is a richer set, so we can infer now locks, barriers, wait notify synchronization primitives. And our procedure is also based on counter examples, but it actually generalizes counter examples, which is a key to tackling interleaving explosion. So, okay. I expected something to show up here. Let me just take a quick look. I will skip that. I was actually going to show you a preview of our technique, but that's okay. So there are broader contributions in our paper as well. This notion of generalizing counter examples is broadly applicable. This notion of doing specification-free synthesis is an important one, where we do not require a user to specify properties. And finally, this also contributed a verification procedure based on language inclusion, which can really be used independently. So I'm sorry that I'm missing that slide, but let me just give you a hint at why I need a language inclusion-based verification procedure. Well, what we are trying to do in this implicit specification is that we say that a programmer writes the concurrent program assuming a friendly non-preemptive scheduler that can only preempt the program at yield statements or when a thread completes execution. Okay, so then the programmer makes sure that everything is working fine in this setting. And then the property of the implicit specification, which is preemption safety, tries to ensure that any interesting behavior that is possible under an aggressive preemptive scheduler that can deschedule a thread at any instant is contained in the set of behaviors that have been ensured by the programmer to be correct under the friendly scheduler. Okay, so there is a language inclusion problem here where you want to ensure that the set of behaviors possible under a preemptive scheduler is included in the set of behaviors possible under a friendly scheduler. This is a much more challenging verification task than the usual reachability task which is associated with verification of safety properties. So this is something you are already familiar with. This is the counterexample guided repair and synthesis framework. Now, I want to show you another way to do this. So notice that in this one, you are, this is sort of a lazy insertion of program modifications. You are accumulating constraints corresponding to program modifications, but not really changing the program in each iteration. And you're waiting till the very end to actually implement all these constraints and changes in the program. Okay, so this is a lazy insertion of synchronization. Another way you could do this is by modifying the program eagerly in each iteration. Okay, and then checking if the verification succeeds. So this is a simpler version of the counterexample guided loop. And while our technique can actually also do the lazy insertion, I'm just going to use this to explain some of the ideas. Now, if you stare at this for a bit, you will notice that this can be too slow. You are only eliminating one counterexample in each iteration. Okay, this can quickly become intractable. There can be really exponentially many or combinatorially many counterexamples. So our solution is to introduce a way to accelerate this iterative process by, in each step, generalizing a counterexample to many other related counterexamples, and then eliminating all of these in one fell swoop in each iteration. Okay, and then in the next iteration, we look for a new unrelated counterexample. So you don't just eliminate one counterexample at a time, you eliminate a generalization of the counterexample. So how do we do this? Let's first look at this generalization procedure. I mentioned related traces. So what do I mean by that? Recall that an interleaving or a trace is essentially a sequence of events from different threads. And I say a trace is related to a given trace if they are essentially over the same set of events. So one is just obtained by the other by a reordering of events from different threads. Okay, so the set of events stays the same. So given a trace, we seek to essentially generalize it to obtain all other incorrect traces over the same set of events that can be obtained by some reordering. Okay, but this can be a large set of related counterexamples. So the key challenge is to actually obtain a way to succinctly represent this entire set of related counterexamples so that then you can manipulate this in various ways. You can use it for synchronization synthesis, you can use it for verification, bug summarization, and so on. Okay, so our main contribution here was to come up with a representation which is called a happens before formula for capturing this entire set of counterexamples that are related to a trace. This is essentially a Boolean combination of happens before ordering constraints between events. And I'll show you in just a second what I mean with an example. So here is, I think, the final example we will see in today's talk. So this is a simple banking example with an initialization thread that initializes the account balance stored in the shared variable val to some value in it. And the pink thread here and the blue thread here are essentially just incrementing the account balance by making some deposits of 10 and 20 using their local variables B1 and B2 respectively. Okay. The assertion here, the safety property here is that the new value of balance must equal the initial value of the balance plus the sum of the two deposits. Now, clearly this program is incorrect. It does not satisfy its specification. So here is one counter example, one trace which exhibits this failure. This is where essentially B1, the event B1 of the blue thread happens before the initialization event, which then happens before B2 and so on. Okay. So the HP formula, the happens before formula that exactly represents this trace is shown here. This essentially is a conjunction of ordering constraints between events in different threads. So this says B1 happens before C1, C1 happens before B2, and B3 happens before A1. We keep the ordering constraints between events in the same thread implicit because this is always fixed. Okay, so this is an exact representation of this trace. Now, what our trace generalization technique has the capability to do is take this trace and then generalize it to a very succinct happens before formula, which captures the essence of why this counterexample was incorrect, which is simply that this event B1 happened before the initialization event. Now, notice that this doesn't correspond to a single counterexample anymore. Okay? It corresponds to a whole bunch of counterexamples or interleavings which satisfy this ordering constraint. So I won't have time to tell you how we do the trace generalization. Let me just mention that we make sure that we preserve the data flow into the error, and we use some minimal unsatisfiability core computations to arrive at this trace generalization. So going back to our example, once we have run through all the iterations of the loop and we are able to succeed with the verification, this is the final happens before formula that we obtain, which essentially captures, each disjunct captures a different mode of failure of the concurrent program. So these are two symmetric ordering violations, and this one here is essentially a race condition, or more broadly speaking, an atomicity violation. So these happens before formulas have many nice properties. The most important one is that it captures all incorrect related traces, in the sense that I said traces were related over the same set of events, and it does not include any correct related traces. Okay, so this is a great succinct summarization of the error in a counterexample. And in our experiments, we found that in most cases, these formulas were very small. So that was trace generalization. Let's look at this step, which is how do we go from a happens before formula to inferring synchronization. Okay. So the main idea here is to essentially identify patterns of happens before formulas that correspond to various synchronization primitives, formulate various rewrite rules that capture these patterns, and then syntactically apply these rewrite rules to transform these patterns into synchronization primitives. Okay, so let me just show you one example rewrite rule which is used to infer locks. So here is a cross pattern between events in different threads, and the rewrite rule says that if you see this pattern, then you rewrite it into a lock that protects access into these respective code regions, A1 through AK and B1 through BK. Now, to get some insight on how we infer this, just note that this represents bad traces. To eliminate them, we can flip these ordering constraints and get this, which essentially says that either BK has to happen before A1 or AK has to happen before B1. Okay, that's what you get from flipping, which is essentially the mutual exclusion that can be enforced by these locks. So we have a bunch of other rewrite rules for wait notifies, barriers, and so on. And we are able to use this to infer synchronization for this original program. And notice that this is fairly non-trivial synchronization, and it's amazing that we are able to do a simple syntactic inference of synchronization for this program once we have a happens before formula. I won't go into the verification technique, which is something that we developed for handling implicit specifications. The rest of this stuff that I explained actually works with either an implicit specification or a safety property. So that wraps up my discussion of these papers. I cleverly managed to skip the drawbacks of my own paper. So it has drawbacks. It shares several drawbacks with the other papers, but there are some that are its own, which is that you cannot always find an implicit specification. We were able to find one in our domain, which worked great, but this is not universal. This verification procedure based on language inclusion is very computationally expensive. So with that, let me just wrap up by saying that we have come a long way in the area of computer-aided concurrent programming. We can handle infinite state concurrent programs. We can handle diverse specifications from temporal logic to implicit specifications. We can infer diverse synchronization primitives. We can do some kind of performance-aware quantitative synthesis, and we have definitely pushed the boundaries of scalability. Okay, but there is a lot more to do, which is great because that means there are several more PhD theses to be written up. So most of the work that I mentioned really focused on assuming sequential consistency. There is also a parallel body of work that assumes relaxed memory models, but there is work to be done in that space. The program models, the performance models are fairly simplistic. No recursion, no aliasing, no complex data structures. This has to be improved. There is no optimistic concurrency control. All of these were blocking primitives. No matter what I said about scalability, it still remains a challenge despite our best efforts. And finally, all of these programs actually assume a fixed number of threads. And I want to mention this challenge because in my last slide, I'll just leave it there. We are trying to target this problem of removing this restriction of having a fixed number of threads in a distributed setting. So we are trying to synthesize coordination for distributed systems such that the synthesized system is correct for an arbitrary unbounded number of processes in the system. With that, I'll conclude.